Sorry, you are not audible. I think your mic is off.
Okay, so let's start the class. Dhruv, how many students are here in this class?
Sir, 84, 85, around
Total
85.
students. So still, I mean, 15, 16 students are absenting.
Sir, allow the DTU's IDs to join automatically, so we will not be required to take permission.
Without DTU ID will be difficult. They will have to get it.
Uh,
Because
Sir, I have DTU ID, still I need to get permission to join this class.
or you can, I will suggest if you want, I can send the link, meet code also. Do you need?
No, sir. Sir, I am saying allow DTU IDs to join automatically, so you will not need to permit everyone for joining.
That feature do we have in this?
Yes, sir.
I didn't see that.
Okay, sir.
But anyway, this is okay. Till I find what you are saying, just explain me how to be. Actually, I'm not so good in this Google Meet, Google Classroom, etc. So this is the Meet code. Somebody wants, you can share in the chat board. Okay. So let's start the class. So we were doing some basics of vector mechanics, vector definitions. Let's extend this a bit more. Let's study some elementary vector algebra and then some good operations, vector operations. Is it clear? All of you are able to see this?
Yes,
Yes,
sir.
sir.
Right? Huh? Okay.
Yes, sir.
Okay. Okay. So here we will discuss first the elementary operations which we discussed in the previous class. Suppose we have two vectors P and Q. We want to find the resultant. Then we can create the parallelogram, and then resultant will be vector sum of P and Q. And we did discuss the derivation even of this particular relation. So here, if you look at this figure, there are two triangles. One is OAC, another is OCBO. Let's come back to O. So OACO and OCBO. Now, if we draw this parallelogram in a slightly different manner, like this. So what we can do here, suppose there are two vectors, P and Q, and their resultant is R. So what do? We start with vector P, say. So we draw OA line corresponding to vector P magnitude and its direction. And then we draw AC line from the head of vector P representing vector Q. And then if you join tail of vector P to head of the vector Q, we get the magnitude and direction of the resultant. Now this is first triangle OACO. We draw it in this manner. Now if we complete this parallelogram in slightly different manner, what do we do on the other side here? Because OA is vector P and AC is vector Q. So what do? We maintain the vector directions in order. So it's like everything is moving in this case anti-clockwise. So O to A, then A to C, and then tail of the parallel vector of OA at C, and then head of P vector at B. So in this order, if we plot, then from B we draw vector Q parallel to AC, but directed oppositely directed. In that case, here we have completed the parallelogram, but the arrow directions in the second triangle are different than the arrow directions in the first triangle. So actually the first triangle OACO gives us the components of a force R. Suppose R is a given force, then its components in the this particular direction where two sets of vectors are there, uh, are P and Q. But here, if you look at in this second triangle, OCBO, the triangle is closing. All the vectors are in order and triangle is closing. So its resultant vector vanishes. So there are three forces here, R, P, and Q. So what do we get from this figure is that it represents the three vectors are in equilibrium, and suppose R is the applied force at a given point and maximum three number of forces are present there, then P and Q will represent the equilibrating actions. Now this is an interesting information. So they will be the reactionary forces which are bringing R in equilibrium. So from the same parallelogram, this is the method we use in structure analysis to get the components and the reactionary forces or the reactive forces using the parallelogram law. So this is the best method in which we don't get the component along the orthogonal directions, rather in any direction we can find the components. So this is one advantage of using the parallelogram, and this we use extensively in structure analysis. Now let's discuss the properties of these vectors. So let's say there are four vectors A, B, three vectors A, B, and C. Earlier we had two vectors A, B only. Now there are three vectors, and R is in fact the resultant. Now these vectors we have drawn in order. That is from O to A, head is at P, from P to Q, head is at Q, and then C is having head at S. So this way these three vectors are in order, and when we connect the tail of first vector to the head of the last vector, we get the resultant of all these vectors. So tail to head method we use when more than two number of vectors are there. Now in this case, you see one interesting property. We compare these two vectors A and V. Their vector sum is A plus B, represented by vector OQ. And in OQ, if we add QS, we'll get R. So OQ is A plus B. Second equation, if you look at, so A plus B plus C is R. That is equation 5 in this text, whatever it is written. Similarly, here you see, if in vector A, if we add this vector B plus C, and B plus C we have obtained from P to S, which is summation of B plus C, B and C. So B plus C is the combined, we have combined B and C here in one small bracket, and then we add on this A, still we get the resultant. So what is this? A plus B plus C is R, and A plus B plus C is also R. This particular means two equality is there. So this equality is called associative property of the vector.
Excuse me, sir. Sir, allow some students.
Okay.
They are pending in the lobby.
Let's discuss other properties. Another important property is commutation.
Excuse me, sir. Sir, I am audible.
Yeah.
Sir, I am saying some students are requesting for entry.
Some students are,
Requesting for entry.
but nobody is visible in my screen.
Okay, sir. Okay.
So whenever he comes, then some beep sound comes, and then I'll allow. Don't.
Okay, sir.
So here what do we do? Say we have two vectors A and B. So OP is representing vector A and PQ is representing vector B. So OQ now, OQ is A plus B. Now what do we do here in this case? On vector, the vector A, in the vector A, we multiply some scalar value M. And so it is a positive value. So OP gets extended. Its magnitude gets modified, but direction remains same because it's a positive number. So OP gets extended to OR. And then here, say we multiply this vector B with the same number M, then B gets extended to RS. Direction remains same, but the triangle changes now. And then we connect OQ, we extend OQ to meet at S. So this new vector we are getting is again that is OS, which is the sum of OR plus RS. Now here we have drawn the two triangles. Now one is external triangle ORS, another is internal triangle OPQ, and here similarity law, because angles are same, so similarity law is satisfied. So from the similarity we can study here that RS over PQ is equal to OR over OP. Now OR over OP is a ratio small m, that is scale factor, that is scaling factor, a scalar value. So from this we find that OR is m into A. And from this relation, we can find from the similarity law that RS is equal to, now I'm just reversing it. Earlier I said, let me draw the geometry, but here I'm saying if we are extending this to OR, then RS is equal to M into PQ, where PQ is B vector. So multiplying factor is same because OR over OP is M. So R, because of the similarity law, RS is equal to PQ into M. So PQ is B, so M into B. Now this way this gets extended. So from this, what do we find? That if we write vector OS, so OS over OQ will be again from the similarity law will be equal to OR over OP, so that is equal to M. So from this we get OS is equal to MOQ. Now OQ is in fact A plus B, so OS is equal to M times A plus B. And we know from the vector addition rule that OR plus RS, OR plus RS is equal to OS. So OR we know is small m into A, and RS is small m into B is equal to M times A plus B. This property is the commutative property of the vectors. So when we multiply the vectors by a scalar quantity, this relation gets satisfied. Now let's do some exercises here, some interesting exercises here. Let's do exercise 1. The two vectors A and B are related to a third vector through some equation. So we have two equations here, and the relations are 6A plus B is equal to 0 and minus 4A plus 2B is equal to minus 8C. Now this relation you will have to use cautiously, but it's a very interesting relation. It's just giving a kind of linear simultaneous algebraic equation. So here we solve it the way we solve simultaneous equations, that B is equal to minus 6A. We back substitute in the second equation the value of B, and we get A is equal to half C. And so from this B is equal to minus 3C. So this kind of algebraic solution we can obtain only when all the three vectors are parallel. This is one very important condition for applying this kind of solution to the vectors. Otherwise, we cannot apply this condition, this kind of solution. 1. Let's do second example here. Any vector C which lies in the same plane of two vectors A and B, and say we can express this. So we have to prove that C we can express as MA plus NB. So what do? We draw the parallelogram. We know vector A, we know vector B, and their directions are known, magnitudes are known. We know vector C. So just extend the line of action of A to meet at P, and line of action of B to meet at R, and the P is the intersection of QP and OP, and R is the intersection of QR and OR, which are drawn. PQ has been drawn parallel to OR, and QR has been drawn parallel to O, the vector A. So from this we compute the parallelogram. We draw the parallelogram, and from this now we can say that OP we can write as some scale factor multiplied by vector A, so MA, and OR we can write as some factor N into B, and then we can say OQ is equal to, that is vector C is equal to MA plus NB. Now let's discuss a third example. This is a very important example, and here it's an interesting example also. From the vector we can find the equation of a line. and this is applicable in case of planes also. This is very interesting relation. It's used in the analysis, finite element analysis, when we apply it in the plates. So it's a very good example. So let's study here. The example is this, that there are two vectors A and B as they are drawn here. So OP and P, let's say this is S. So PQ is vector B and OP is A. So what it is saying, that if we connect the vector C to the middle of vector B, then we can say that from our studies we did earlier, that vector C is equal to A plus half B, right? Now suppose this midpoint R is not exactly at the midpoint R, rather it is at some other location. So this relation can be modified as we studied, that C is equal to A plus MB, right? Now here vector C, suppose we know the coordinates of point R on this vector PQ as xy, then C vector we can write, because if we take O as the origin, C vector we can write as xi plus yj. Now let's see this figure in the Cartesian coordinate system. Vector C is being represented by OR. O is the origin, so OR is xi plus yj, and its inclination with the x-axis is alpha. So from this we can say y is equal to x tan alpha. That is one equation. Now suppose there is a line on a vector V which is on vector V. So line PQ is there and it passes through R. So PQ makes an angle theta with y-axis, and in the intercept is C. So vector OP is A, which is having length C. So if we transform this relation for y, we can say y is equal to x tan theta plus C. So we got another relation for y. First relation was y is equal to x tan alpha, and y is equal to x tan alpha is the equation of a line on which vector C lies, and y is equal to x tan theta plus C is the equation of line on which the vector B is lying. So if vector C represents the position vector rather for point R, where R is lying on vector B, then what we can say, that this vector C represents the equation of this line PQ. So because y is equal to mx plus c and x tan alpha is also equal to y, so we can say here that xy, they represent the coordinates of point R, and the vector C in fact represents the equation of line x tan theta plus C. That is one very interesting result. This is used in a different way, but that we will study later. A third example here, fourth example here, that here we have say two vectors, vector A and vector B. A is OP, and vector B is PQ here. Now same exercise we are doing here. Say OT is connecting the middle point of PQ. So then we can say that OT is representing vector, say here is S point rather. No, not S. It is OT. Let's say then OT will be A plus half B. So OT is A plus half B, and from this we can define OS vector. That is some multiplying factor, is scalar multiplying factor on OT. So n times A plus half B. Here we define vector PS. Now PS is in the opposite diagonal. So what this exercise is, that if there are two vectors and one there are a line drawn from the vertex of this figure, vertex O of this figure, to the midpoint of the opposite side of the parallelogram, then it divides the opposite diagonal in the ratio of 2:1. So this we have to prove. So in this case here, the PS vector we define, which is in the opposite diagonal. Now because PS is equal to A minus B, as we know from the definition. So PR is A minus B. So we can write PS is equal to M times B minus A. Now we pick this figure OPS, separately draw it here. So OPS is representing a triangle of forces, and here OA is representing A, and PS is representing M minus B, M times B minus A, and OS is representing N times A plus half B. So here what we can say, a general relation will be, a condition equation for this will be A plus PS is equal to OS. Now A plus PS is M times B minus A is equal to N times A plus half B. Now if we rearrange these vectors, bring A vector on the left side, B on the right side, we get this equation that A times 1 minus M minus N is equal to B times half N minus M. Now here we studied one very interesting property, that this kind of algebraic modification in the vectors can be done only when the two vectors are parallel. All the vectors are parallel, but here these vectors A and B are not parallel. So this relation is not valid. It means what? This equality will exist only when the multiplying factors, the scalar multipliers, are individually 0. So 1 minus M minus N must be 0, and half N minus M must also be 0. So from this we get two unknowns, and there are two equations, two unknowns M and N. We solve it. So N is 2 by 3, M is 1 by 3. So we, from this we identify that this length is 1/3 of the entire opposite diagonal. So this divides, point S divides the diagonal PS in ratio 2:1. Now these are some exercises. We'll use them later in our analysis. Let's discuss the sine rule. Sine rule also you have studied, you must have studied, and that is for geometry, triangular geometry. We can apply the sine rule, but this can be extended to vector calculations also, and this we use to our advantage nicely when we analyze the trusses. That time again we'll discuss these sine rules, apply sine rules, and get the solutions. So this is known as Lemie's theorem. And here there are three vectors, let's say, representing these three sides of this triangle. AC is vector B, and the CB is vector A, and BC is vector C. And the angles between these two vectors are, say, angle A, angle C, and angle B. Let's drop from vertex B in normal on vector A, vector B. This perpendicular length is HB. So from this we can prove that HB over C is sine A, and HC over C is also sine A. That can be drawn obtained from this geometry. Similarly, sine C from this geometry is HB over A. Sine B from this geometry is HC over A. So from this we find, if we equate, work out in terms of HB, so then HB, one relation is C sine A, another relation is A sine C. Similarly, SC is A sine B and B sine A. This equality is there. So C sine A is equal to A sine C. So C over sine C is equal to A over sine A. So actually here we are not getting the directions, they are scalar magnitudes. Basically these triangle sides are scalar magnitudes. So this way here angles are known. So we can apply this to the vectors also to get their magnitudes. Solution of these vectors. This is known as Lemie's theorem. So from this, if we combine the two relations, it is A over sine A plus B over sine B plus is equal to C over sine C. Inverse is also used. Sine A over A is equal to sine B over B is equal to sine C over a small c. And these A, B, C's are representing the magnitudes of these vectors B, A, and C. So this also we'll use extensively later. Let me define unit vector here. Unit vector definition, Kraszik. If you have gone through Kraszik engineering, advanced engineering mathematics, that's a very good definition is there, but that definition at the moment I'm not taking. That's a little advanced definition. Here, simple definition we are discussing here in this course. So unit vectors here in rectangular Cartesian components, as we know that we can multiply a scalar value to a vector to modify the vector, same vector, magnitude, direction will not change in this case because it is a positive, and then we can divide also in the magnitude by some scalar quantity. Now suppose the m value is the magnitude, which is actually the magnitude of this vector A. So if we divide vector A by m, then it will be vector A divided by magnitude of A, this will result in a unit magnitude vector. This vector will have the same direction, which is the direction of A, and its magnitude will be unity. So this vector we define as unit vector. And unit vector nomenclature we use to define along the rectangular coordinate axes, Cartesian coordinate axes, x, y, z, o, x, y, z. So I along x, j along y, and k along z. So these are the definitions we use for defining the unit vectors along the respective axes in the Cartesian coordinate system. Now let's extend this definition to get the to represent a vector in 3 dimensions. So here, say we have a vector A. This box has been drawn just to represent this parallelepiped diagram. So just to represent this vector components. So along x-axis, its projection is ax. Along y-axis, it is ay, and along z-axis, its projection is az. That is the component. So OP here is AX, PQ is AY, and QR is AZ. Then we can write in terms of unit vectors, because A is the vector sum of these 3 vectors. So first vector, second vector, and third vector, the vector sum resultant of these 3 vectors is A. So in terms of these unit vectors, we can write as sum of AXI plus AYJ plus AZK. We sum all the 3 and we get vector A. And here, to get the magnitude of A, we can, there are 2 vectors in the same plane, the AX and AY. So let's say that is the resultant of that vector is A, resultant vector, that is diagonal on this box, which is behind this front box. So in this, it is A1 is the square root of AX square plus AY square. And then that diagonal plus this Z will give us the magnitude of A. So it is A is equal to the square root of A1 is square plus AZ is square, and replace A1 is square by X square plus AY square. So A becomes equal to square root of AX square plus AY square plus AZ square. This we represent as the magnitude of any vector in 3D space. It can be reduced to 2 dimension XY also to represent this vector space, vector magnitude. Now some interesting relation. So let's extend this concept to determine the direction cosines or define the direction cosines. Actually, we have discussed that I, J, and K are the unit vectors along the respective Cartesian coordinate axes. But a general definition which is used in vector mechanics is Ex, Ey, Ez. These are the standard bases we use. So standard basis, I is Ex, J is Ey, K is Ez. Now this helps when we take Ex, Ey, Ez to define along any axis the 3 components of a vector. So it's a better approach to use Ex, Ey, Ez instead of I, J, K. But in general, when we are dealing with the rectangular Cartesian coordinate system, we'll revert back again and again to I, J, K. So here, Ex sometimes Ex, Ey, Ez are used as Ex hat, Ey hat, Ez hat. So hat symbol is also used as accent which is accented on this Ex. So that you have to, you can use, some text use that also. Here we define, so suppose this vector A is here as we define using this box, 3D vector, then its X projection is Ax. And so vector on x-axis, the vector component on x-axis of this is Ax, Ex. Let's say it is Ax, Ex. And similarly, vector component on y-axis is Ay, Ey. Vector component on z-axis is Az, Ez as drawn. So Ax, Ey, Ez are the magnitudes. So if we define the angle between the vector A and the x-axis, are the x component and alpha, then between y-axis and the A vector is beta, and then with respect to z-axis, this inclination of vector is gamma. Then cos alpha, cosine of that angle alpha is actually here. If you look at this plane is perpendicular, so then this cos alpha can be defined as we take the dot product of A with Ex, a unit vector directed along x-axis. So A dot Ex gives us Ax. So A dot Ex, so angle between Ax and A is alpha. So that cosine of that alpha we can define as ax ex divided by magnitude of a. So a dot ex is ax. So ax divided by square root of ax square plus ay square plus az square is cos alpha. Cos alpha we take as a one typical value and we define it as say L. So most of the texts use this L, M, and N as the definition for direction cosines. So L is cos alpha, M is cos beta, and N, this is N actually, not L, it's a typing mistake. So this is cos gamma. We can obtain M and N in the same manner. And we know the relations here, cos square alpha plus cos square beta plus cos square gamma is equal to unity from the trigonometry. So then L square plus M square plus N square is equal to unity. So direction cosines, when we sum them, the squares of the direction cosine, we get unity. This is a very good important condition equation. So now we can replace here AX by magnitude A into L, AY as A into M, and AZ as A into N. So we can write it like this, that vector A is 8Li plus AMJ plus ANK. Now A is a constant scalar multiplier here, magnitude, so we can take it outside. So A is into in the square bracket Li plus Mj plus Nk. So vector A can be written in the direction cosine terms also. This is a very good and very important way to define a vector. Now this Li plus Mj plus Nk, actually i's are the unit vectors along I, j, and k. So they are here to represent A. This particular vector we get as the summation of these three vectors is one vector, a unit vector directed along A. So there is another variable we use here. It's a very good approach to define a vector that you will find that will study in mechanics of solid. There you will do it extensively. So this vector n, boldface n, is different from this direction cosine n variable. So just take it as it is, because n is also used to define this vector, unit vector along A. So A is the magnitude, and unit vector along A directed like this is equal to, this unit vector is Li plus Mj plus Nk. So this is another way to define a vector A here as magnitude into a unit vector along A. Now we'll use these definitions and do some calculations with the vectors later. Now here, so from this definition, we can say suppose vector B is there, V is there. It has an inclination theta with respect to x-axis. So using the direction cosines, we can write this as V is equal to magnitude of V into cos theta I plus cos pi by 2 minus theta I. And cos pi by 2 minus theta is the angle of this vector with respect to y-axis, that is beta. So it would be sine theta j. So cos theta I sine theta j here is the unit vector along this vector V. So magnitude of V into cos theta I plus cos theta j represents this vector V. Sometimes the gradients in terms of this theta is not given, rather the slope of the vector is given in terms of the gradients, 3 vertical is to 4 horizontal, or 4 horizontal is to 3 vertical. In surveying we use this kind of concept. So for 1 vertical, how much is horizontal distance is traveled. So here this vector V we can represent using these gradient data also, and that is here because cos theta now will be 4 by, if we find the hypotenuse here, that is 5, so 3, 4, 5. So cos theta will be 4 by 5 and sine theta will be 3 by 5. So cos theta is 4 divided by square root of 4 square plus 3 square, and sine theta is 3 divided by square root of 4 square plus 3 square. So 4, this is again 4 by this I plus 3 by this term I j is equal to multiplied by V gives the vector. A third way to represent the vector, at times we know the location of these vectors. So both ends are connected to some machine somewhere. So their coordinate positions are known. So instead of getting the theta, we know the coordinates. So from the coordinates, we can find out their x projection and y projections, and then find out the length here. So length of the this vector here, length terms, then we can define cos theta and sin theta in this fashion. 9 minus 2 divided by square root of 9 minus 2 whole square plus 6 minus 3 whole square. I plus 6 minus 3 divided by square root of 9 minus 2 whole square plus 6 minus 3 whole square j multiplied by v is vector v. So these are the three ways to define or represent a vector. This information is given in Weir and Johnston, so you can refer Weir and Johnston and do a lot of exercises are there, so you can attend. Now, just leave the vector mechanics at the moment here. Let's go to the forces definition. So, characteristics of forces. Now, forces, as see, this box is being pushed by this person, or it is being pulled by this person. So, this kind of force is called pull, and this force is called push. So, in this box, you see force vector is F. And here, one important thing is that point of action, where point of application is rather of this force, is also known or should be given. So force needs magnitude, force needs direction, and third is it needs the point of application. And direction itself will define its line of action also. So basically these four parameters, four specifications we require to define a force, like magnitude, direction, and point of application. But the direction is associated with the line of action. So basically we require three specifications: point of application, direction, and magnitude. If any of the three specification changes, the force effect will change. Force will change. So these are three basic specifications for defining a force. Now different forces, so this we define as the characteristics of forces. Different types of forces we use in the analysis are physical phenomena. One is called push and show. Show is a strong hard push. Press and pressing, touching, kicking versus pull or tug. Heave is a strong pull, hard pull, and drag. Wind drag. When wind forces are there, then during rainy season we experience very strong winds, and on the surfaces of roof, etc., they apply a kind of force which is tangential to the surface, that is called drag force. So drag force, all these things we'll use somewhere, some examples that I will discuss again. So here drag is a contact force, which is so here we define another term here that is called contact force. Force occurring when two objects touch. It's like here there is one contact force between the box and the surface. That force, when you are pushing it, so when you are pushing, there are two objects. One is this person and another is this box. So between the two, there is an interaction. Between this man and the box, there is an interaction. So that interaction is because of this contact, because of this touch. So we call these kind of forces as contact forces. Then non-contact forces are basically the magnetic forces and gravity forces. These are the forces which get applied in the body without touching it. So it's a gravity force or magnet force, non-contact force. Balance forces, when two forces are equal in size and opposite in direction. Suppose one person is pushing this and another will start pushing in the opposite direction, then this will become a balance force if this box doesn't have any deformation. It doesn't have any deformation, then it will be a balanced force. Unbalanced force, when forces are unequal in size, whether in the same direction or they are in opposite directions, the moment you apply the force, it will cause acceleration in the body. So it will cause deformation. So it means such forces, when body deforms from one state to another, like from rest to moving position, it will be subjected to a kind of unbalanced forces. Now let's discuss some force examples and then we'll do some numerical examples here. So a force system here, we express the magnitude like P, direction using this angle theta, and the point of application using another subscript wherever this force is getting applied. So a vector requires magnitude and direction, normal vector, a mathematical abstract quantity, but when we define force as a vector, it requires three terms, P, theta, and A, the point of application. Now suppose this bracket is there, we are using for some supporting, for connecting some cable, like in suspension bridges, one cable runs and gets we connect it at some location with this bracket, then this cable applies some force, which is tensile force. So actually, I'm not going into the basic definitions of actions, reactions, and internal actions, but just briefly, let's discuss it here. So the force which is getting applied externally is called cause or external force. This force is known as applied force. Now, to resist this applied force and to maintain the integrity of this bracket, what this bracket does, it opposes the force applied by the cable. So that opposing force is called reaction. So this may be a foundation, a bolt, or somewhere tower which is connecting this, in which this box or this bracket is connected. So they offer some reactionary force. So those forces are called effects, and the applied force is called a cause. So there is known as law of cause and effect, and that we will study later. At the moment, it's not required. So these are the effects. Additional effects will be seen in the body. Suppose it's an elastic body, then there will be deformations. So the cumulative effect of deformation is called cumulative effect of deformations are defined as strain displacements. So here there are deformations. Now how many deformations? There in civil engineering, in structural analysis, you will study 4 types of basic deformations: because of axial force, because of bending moment, because of shear force, because of torsion, and then there will be straining pattern. If you have seen finite element solutions, and then you might have seen these contours of strain contours somewhere. So straining is there. Sometimes permanent strain comes when stress gets exceeded by the yield stress. There will be some permanent deformation, or residual strain will be there, and it all depends on the material which has been used to manufacture, to create these brackets. So these effects are called internal effects or internal effects. These are because of the internal actions. So internal actions are stresses here. So the effects of stresses will be, because of the strains, there will be stresses, and then we get some resistance. So cumulative effect of these stresses is the reaction. Those things you will study later. So this is how we define the forces in for the analysis purpose. This force is a fixed vector. It is fixed vector because point of application is fixed. We define various types of forces. So in 2-dimension and 3-dimension, we define these forces. In 2-dimension, we call them as coplanar, and in 3-dimension, we call them as non-coplanar. So a system which is getting subjected to these set of forces is known as coplanar system, non-coplanar system. Now, coplanar forces are systems it may be like collinear force. Their line of action are magnitudes. Line of action is directed in the same direction. Parallel forces, when they are parallel. Concurrent forces means there are multiple number of forces and they are coincident at one common point. Now, those kind of forces we call as concurrent forces. They might not be acting at one point. Suppose there is a big structure, big rigid body like a beam, then at different locations there may be forces. So those forces we define as non-concurrent forces. And non-coplanar forces may be parallel, may be concurrent, and may be non-concurrent. Few examples I just want to explain here. A 2D example of say beam on elastic foundation here. Some 4 forces are there. They are parallel forces. Here you see there is one body. Again, it's a 2D body. The force P, Q, and R, they are not exactly acting at the point O. Rather, they are acting on the surface of this body. But when we extend the line of action of these forces, they meet at common point. So it means they are concurrent forces. Here you see truss example. It's a 2D truss. In this 2D truss, roof truss, you might have studied somewhere in engineering drawing. So there are multiple number of forces at different locations. Here at top, you see there are two forces which are concurrent here, but these forces are not concurrent with other forces. So other forces are non-concurrent. But here they are coplanar. They are all in the same 2D plane. Here, so this is the example of coplanar concurrent force. This is the example of coplanar non-concurrent force. These are collinear forces, coplanar non-collinear forces. These are parallel forces. Then let's discuss the 3D example in which at the origin there are three forces on different planes. So they are non-coplanar concurrent forces. F1, F2, and F3 are non-coplanar concurrent forces. Similarly, in this example also, these concurrent forces, their components have been obtained and drawn in this with the resultant. So, and here this is the parallel forces. Four columns are resting on a mat foundation. So there are four applied loadings are there on the columns. So these four forces we define as non-coplanar, non-concurrent forces. Now, the concept of parallelogram we can extend to 3D. We can create a parallel 5 geometry and we can find the resultant in the same way. So here there are F1, F2, F3 which are non-coplanar concurrent forces. So their resultant also we can find in the same manner by drawing this 3D geometry. But drawing this 3D geometry is not an easy task. So actually we don't use this method, graphical method, to get the resultant, but it can be used. We'll discuss in space trusses later. One space truss example is this, in which the two forces are there. One is 80 kilonewton at joint E and 40 kilonewton in the direction, say x direction, say y direction it is. So in x direction, one is 80 kilonewton, and in y direction at joint E, it is 40 kilonewton in this space truss. So these forces are non-concurrent, non-coplanar. So these are the examples of 3D forces. Now here we have the force system. So let's study a bit more the 2D force systems, the concurrent forces. So concurrent forces, actually we have discussed the parallelogram. So there are two forces which are concurrent at point A. So F1 and F2 are the two forces. Their resultant is say R. So how do we find the resultant? In the same manner, we can complete the parallelogram and then F1 square plus F2 square plus twice F1 F2 cos theta. If you know the deviation angle of vector F2 with respect to F1. So in this case, second figure, if you look at point of application of F2 and F1 are different, not exactly at A, but if we extend their line of action, that means at A, then we can say that these two forces are concurrent and they are coplanar, they are in the same plane. So their resultant we can find using the parallelogram. So this approach we can apply here. From A we can draw vector F1, then along F2 we can draw from the head of F1 vector F2 and connecting the tail of vector F1 to head of vector F2 we get the resultant. And this is the triangle law on parallelogram law we can apply. Here there is an application of law of transmissibility also, you can say, because what we have done here actually in this course, we have extended the line of action, or rather we have shifted the force point of application on the same line of action. F1 has been shifted on the same line of action. So from this point to A, similarly F2 has been transferred or transmitted from this point of application to A. So this is known as the law of transmissibility. This we'll discuss a bit more a little later or maybe later. So here basically we have discussed the components of force R which can be determined along any two directions which might not be orthogonal. So here F1 and F2 are defined as the components. Now here you see in this figure there are two other forces there are FA and FB. FA and FB have been obtained by dropping a normal from the head of R onto the line of action of F1, and FB has been obtained by dropping a normal from head of the R on the line of action of F2. So these FA and FB are known as rectangular projections. These are known as the projections. Basically, we call them as projections of the resultant force R, and F1 and F2 are known as the components. Now, F1 and F2 will be equal to FA and FB respectively when the angle between the two forces is right angle. If they are perpendicular, then these two, the components and the projections will be equal. Otherwise, they will not be equal. And the vector summation, we know that FA and FB will not be equal to R. Let's do one exercise here. In this bracket, there is a force F here and at an angle beta with respect to y-axis. Now, coordinate axis has been drawn like this: x positive in this side, y in this direction. So fx is f sine beta, fy is f cos beta. So we can resolve them in these two mutually orthogonal directions, x, y, taking their sine and cosines. So here this beta is there, so we can find out pi by 2, pi minus beta, this angle, acute angle, and then the component will be f cos pi minus beta along y-axis, and along x-axis will be f cos pi minus sine pi minus beta along x-axis. So this way we can derive these components. Similarly, in this figure and in this figure, here there is a deviation angle of this portion of the bracket with respect to original portion is some angle alpha. So net angle to find the component of f along x and y will be along x will be beta minus alpha. So then f cos beta minus alpha along fx and f sine beta minus alpha along fy. So this kind of exercise you need to do and attempt from so many problems using book by Hibbeler or using this Beer and Johnston. Beer and Johnston is available for free in the net. So you can search in the net. There are 700, 800, or even more than that pages available. Old versions are available. You can download it and study it. Very good book. Now here, let's say we have an example, but this example we'll discuss in the next class tomorrow. Let's stop here. Thank you.
Thank you, sir.
So please write something on the chat board so that I'll mark your attendance. Which link you have sent here, Dhruv?
Sir, attendance link.
Attendance software link. I'll download it later. Don't worry.
Okay.
I'll let it be there. I'll copy it. So please write something on this chat board. I'll copy it for attendance purpose.
Sir, please share the PDF to me so I can
I
provide
don't
it.
give PDF to any class. That's the problem.
Sir,
But I'll suggest you better download the book. It's available for free, Beer and Johnston. And once you will see the Beer and Johnston, you will not require my notes,
okay, sir.
right? But still, if you need, then you'll have to ask me which slides you require, and those slides I can copy and give it to you, right?
Okay.
But not all the slides. There are NPTEL notes. There are people, a lot of faculty members of IITs have generated these course notes, PDFs. I mean, PPTs are there. So you can download those. Same thing you will see in my notes also. There won't be much difference. But still, if you find any difference, you can ask me. I'll provide. But you will have to ask me specifically. Okay, this topic slides we don't have anywhere. Please provide us. Then I'll give it. Definitely. Thank you.
Thank you so much, sir.
Okay.
Thank you, sir.